All right. I think we're almost good. All right. So we were talking about. I think the last thing we talked about was unit vectors and frame. We only talked about unit vectors and a little bit of matrix multiplication. So, as a general advice, you will see we'll deal with matrices and vectors a lot. So, if you need to refresh your memory a little bit about how does matrix multiplication work, I would strongly suggest you do that. We're going to do a lot of matrix multiplication, at least by hand. Later on, we use Mathematica to do a lot of these works, most part of the process for us. But still, we need to be able or be comfortable with working with matrices, 3 by 3 matrices at least. Then we'll go further. You will see we have to start working with 4 by 4 matrices, which obviously. Yes, Pamela, go ahead.
Sorry. Do you post a notes for this? I know you posted like the lectures, but do you post like the PowerPoint presentation that you?
I think I did. Let me double check. Let me see what.
Also, good morning. Happy Monday, everyone.
Good morning. Happy Monday to you too. Mondays are a little slow, so I guess. All right, so let me see the course robotics there. So I did post a lecture which includes the video and the notes.
Okay. I see it now.
Just click on that. You should all be able to have access to the notes. So,
Yeah, I see it now. Thank you.
so good. Yeah, if you don't, just shoot me an email. I believe I said in a way that you should have access. So should work.
Thank you.
Of course. All right. So we're talking about before Pamela interrupted me. I was saying that we were talking about unit vectors in our last class, and we kind of looked into multiplication, cross product, dot product, multiplication of like working with vector matrices. I have to have some. Working with matrices and how to do multiplication, finding determinant, finding the inverse of a matrix. But usually, what comes the most, I would say, what comes handy the most is just matrix multiplication. The other ones, we probably end up using the software to do that, especially when we get into 4 by 4 matrices. That's not going to work. Just finding the inverse or determinant of 4 by 4 matrix is just too long. All right, so in order to get things started and we look into, again, as we said, robotics is a very multidisciplinary field. So we are going to be very focused on industrial robots, specifically the first generation, the robots that are fixed in a place, and they're mainly doing different types of operations in, let's say, manufacturing and assembly lines. And in that even category, we only focus on, well, we're mechanical engineers, so we mainly focus on, or only focus, I would say, on mechanical engineering aspect of it. And again, to make it even narrower, we look at the kinematics mostly of those arms, robot arms, and how we can actually study the motion, how can we figure out where each part or each specific joint or each link is at any given moment, and how can we actually define or design a path for specific motion for a given robot arm. So it's relatively narrow what we cover in this course if you think about the whole field of robotics. So to get into kinematics and look into how to study motions, we're we have to start, we have to lay, I would say we have to accept, or we have to come up with some common notations and how do we represent things in this course, right? To study the kinematics. So the natural next step would be talking about frames. In this course, you're going to hear me a lot talking about global coordinate frame and local coordinate frame. So we usually and typically I talk about these two a lot. I mention and refer these to these two a lot. So what happens is that typically we have some fixed frame or global coordinate frame. Global coordinate frame doesn't have to be necessarily a fixed frame, but usually have a global coordinate frame and a local coordinate frame. And we're looking into how can we find the motion of a specific particle, or better to say a point, or a joint, or a part of a link, in how to represent the motion or the position in both coordinate frames. So to get things started, let's just talk about frames a little bit, or what in terms of frames we're going to deal with in this course. So frames, basically, again, these are not new, but we define a coordinate frame by a set of unit vectors, right? In typical Cartesian coordinate system, you have x, y, z, and you define that with we define the coordinate system with I, j, k unit vectors, or basis vectors as they call it. As long as you know those vectors, you can identify your coordinate system. They have a length of 1, right? We already know that, and these are not new. But just to get the notations right, I will just introduce things. Introduce two coordinate frames, let's say x, global and local coordinate frame. I don't know why I'm so. So, let me just put it here. A coordinate system can be defined by, let's say, a set of unit vectors or basis vectors, so if we have, or let's call this, let's go with 2. I'll define one coordinate system here. These are what we deal with this in course a lot, so let's get things out of the way by defining them. X, Y, and Z. And then let's define another coordinate frame. Let's use a different color, why not? I'll do it this way. X, Y, and Z. So that'll be X, Y, and Z. So if I have, let's say I'm looking at a specific point, right, P right there. Let me also put the unit vectors there. So let's use X, the unit vector for this is I. I'll use uppercase I for global coordinate frame, J and K. And this is represented typically by G as global coordinate frame. This one is represented typically as B, body frame. Also, we refer to it a lot as local coordinate frame. Body frame, because what happens is that if you think about a robot arm, we need a fixed frame to study everything with respect to it. Some were fixed. And then we need a frame that we can attach to, let's say, a part of an arm, and then study the motion of a specific part of the arm. So That's why we refer to that local coordinate frame as body frame. We represented that with B. You hear me a lot referring to that as local coordinate frame, not body frame, but they're the same, body coordinate frame and local coordinate frame. And that one, unit vectors, you can represent by I, J, and K. So, few words there. So G frame or label or G frame or fixed frame, you can put it this way, is that doesn't make sense if I go it that way. So G represents a fixed or global coordinate frame. This way. B represents body, present the body or local coordinate frame. Now, the way we represent it, when obviously we write equations or when we refer to them, we go with G O X Y Z or G X Y Z, or well, let's see, follow it, X Y Z, or just simply G. And the same story for B. We can just go with B. I have to also note that this is O and this is O, where the origin is. So B O X Y Z or B X Y Z, or you just use B, right? Uppercase B. So the position of a point, like point P of, let's say we are dealing with a rigid body, right? One specific point on this rigid body, the position of point of P, which is part of the body, like rigid body, we can represent that as, let's put it this way, in the position. We can just represent that in both coordinate system, right? In the position of a point P on point P on rigid body B in, all right, in local coordinate frame, right? We can just say R. Let me go with local coordinate frame. You can say RB. Should be blue. You can say RB, right? You can say RB is equal to X, right, I plus Y J plus ZK, right? Some coordinate. Right? You can just think about it as, let's put it this way. This is RB. Right? This is R. Just separate it. RB. That's where the point P is in local coordinate frame. Now in global coordinate frame, we just use R and then we use the notation G. This way, we say RG in position of point P in global coordinate frame is basically just X, I plus Y, J plus Z, K. Right? and that's this vector. If I refer to it in this coordinate like this would be your RG. So I'm just trying to show what are the notations we're going to use when we deal with these two coordinate frames that we basically use a lot during this course, introducing different types of motions when we go through the whole kinematics problem. So we can write this in a vector form. All right, if you can think about RB as a vector like this, X, Y, Z. Sometimes I represent that as X, Y, Z transpose, meaning that it's basically vertical. I'm just writing it horizontal because sometimes it saves time, it saves space. So I write it horizontal, put T as transpose. And RG, similarly, X, Y, Z. I can sometimes I also represent that with X, Y, Z transpose. So RB is basically the RG is the position vector expressed in frame G. RB is the position vector expressed of a position vector of point P expressed in coordinate frame B. So that's what I am trying to say. This is position vector in frame B, which is local frame or body frame. And this is position vector in frame G. Okay. So this is pretty much our notations. These are what we use a lot during the course, going from one frame to another. We're studying the rotation, we're studying the specific motion. How can we use body frame and global coordinate frame, or local frame and global frame, to find the relationship between different coordinates, or better to say, find the relationship between coordinates in different coordinate systems. All right. Hopefully this makes sense and establishes a general understanding of what we're going to use for notations. Now, just keep in mind that sometimes I also use this. Sometimes I say, well, this is RB for point P, right? RG in point P. Sometimes I do that. Sometimes I say RB for point P, meaning that this is a position vector for point P in global coordinate frame. This is a position vector for point P in local coordinate frame or in body frame. So I do use P when I'm referring to a specific point, right? Depending on what the name of what is the name of that point. In this case, is point P, could be point Q, so that would have been RQ. That's where I put different, I would say, letters to represent or to provide a good understanding of what does that vector or what does that specific letter represent. And technically, these are vectors. So just to be correct, these are vectors. All right. Now, once we are comfortable with the frames that we're using, now we can actually start looking into kinematics. Now, in order to look into kinematics of robots, it's easier if we break it down into rotation kinematics, meaning that a situation in which the rigid body or body frame only rotates with respect to global frame. Right? So you can, obviously this is a three-dimensional space, so you can have a rigid body moving around and rotating, right? You have three X, Y, Z coordinate to move, and you have three rotations around, you have one rotation around each axis, X, Y, and Z. So that's general form, general motion in three-dimensional space. Now, to make it a little more, I would say, easier to understand or follow, we're going to break it down. We start from rotations, meaning that body frame and global frame, or local frame and global frame, their origins are on top of each other, and the only kind of motion that is allowed is basically a rotation about a specific point, rotation about an axis, let's put it this way. Then we move from rotation to general form that includes both rotation and translation. If you think about it, think about global coordinate frame G fixed and body frame attached to a rigid body, so your rigid body can move wherever it wants and can rotate. First, we're just going to talk about rotation. There is no translation in any possible in any direction. All right, so let's look at that. So rotation, kinematics. I'll put it this way to follow textbooks way of referring to it. So this case, we have a rigid body, right, with a fixed point, and rotation only occurs during around this fixed point, right? This rigid body is only allowed to rotate around this fixed point, if you think about that. So there are three possible rotations. It can rotate around x-axis, y-axis, or z-axis. Right? Any other rotation that occurs, we can basically think about it as a combination of these three rotations. Wherever you want to rotate ends up, there are components, rotations in x, y, and z. You will get to that point in terms of where it ends up after that specific rotation. So only rotations are allowed. That's what I'm trying to say. Let's put it this way. Rigid body, or we have a rigid body which is rotating about a fixed point. That's pretty much it. That's the only type of rotation or motion is allowed. So let's look at the rotation about each axis separately, right? We're going to start with rotation about z-axis. And remember, rigid body, when I refer to rigid body, it means coordinate frame B, right? I said body frame or local coordinate frame is a frame. This B is the frame that is attached to rigid body. So that frame moves with rigid body. In this case, it rotates with the rigid body, Global coordinate frame is fixed. So let's just to remember, rigid body means local coordinate frame. Coordinate frame or body frame B. And then we have global frame G that is fixed. So let's go with rotation about, start with a rotation about Z axis. So initially, what I'm trying to say is that we have a situation like this. We have a frame. Let's put this. We have a frame like this. This is my global coordinate frame. This is G, so I'll represent it with Y and X. And coming out of the screen would be your Z. And then we have our local coordinate frame. Initially, they're just sitting on top of each other. So this is X, this is Y. This would be your X, this would be your Y. Should have drawn it probably a little longer. There you go. It's a little better if I do it this way. So that would be your X and Y. If you have a point P1, somewhere right there. Say this is point P1. And let's say this point is, this is the vector for the point right there, is R1. This is R1. R1. Representing where this point is in this specific situation. Now, in this initial situation, right, if we have this as, like, these are the components, you pretty much get the same component for local and global coordinate frame, right? You get, if I call the position on x, x1, you get x1, x1 is equal to x1, right? Wherever the x is in local coordinate frame is the same as x in global coordinate frame. The same story for y. y1 is equal to y1. So if you want to write R of represented with BR1 is pretty much is your x1y plus y1j plus z1k. Z1 is just, we're in the plane for now. Rotation occurs around z, so you don't really see z here, but it's just coming out of the screen. R1 in global frame would be xi, right, x1i plus y1j plus z1k. This is just step one. Nothing has happened yet. Right. Now what we do is that we're going to rotate. We're going to rotate this body, which means rotating local coordinate frame or body frame, alpha amount around z. Right? So this is xy, uppercase x and uppercase y are fixed. What happens? We rotate lowercase x, lowercase y, or body frame alpha amount. Alpha amount. So this is what happens. We get our, I'm going to put the global frames here. I'll just draw it a little larger so we have to use a couple of notations and write things on it. So this doesn't really move. This is y and this is x. This is fixed frame. What moves is your x and y. So this one, hopefully draw it perpendicular. This moves. And that would be x. This would be y. Might be able to make it a little longer in this direction. We are rotating alpha amount, so this is alpha. So point P1 that used to be here, it was here before. I try to be close as it used to be here, P1, represented by R1. This being R1. Probably don't need that, but hopefully things don't get very crowded. And now it's rotated, and we have it, let's say, somewhere here. I'll call it P2, where the P1 is, or point P is at initial moment P1, let's say point P at final moment. Somewhere here. It's hard to guess that, but let's say it ends up being somewhere here, P2. Now it has vector R2. So this turns out to be R2. All right. So what we want to do is that we want to write the, so we have a rotation about global z, right? Around z we have a rotation about alpha amount. Now we want to write the new global coordinates based on local coordinates. Right? Here is what we have at after alpha rotation. Here is what we have. We have R2. Let me just sake of completeness. We have R2b in local coordinate frame. Position of that is x2i, let's say y2j plus z2k, and that is, let me try to show them on this. So if it's P2, right, P2 gives you this on local coordinate frame. So this is your x2, this is your y2. And you have the position in global coordinate frame. That would be x2i plus y2j plus z2k. In global coordinate frame, I'm trying to refer to these values here. Let's say this is your x2, this is your y2, right? Now remember, lowercase x2 and lowercase y2 are the same as lowercase x1 and lowercase y1, right? Point P, this frame is attached to the rigid body. So when it rotates, that point P is still in the same position with respect to your local coordinate frame. So these are the same, just x2 is the same as x1 and y2 is the same as y1. But uppercase x and uppercase 2 for point 2 changed, right? They are here. We know where they are, but they used to be here. I am running out of colors here. They used to be here. Yeah, you can't see yellow there. Used to be here. So this was x1 and this was y1, right? So again, to understand what's going on, we rotated the body, which means we are rotating a local coordinate frame, alpha amount. Now, when we rotate that, the new coordinates, we wrote the position vector for new for where the point is after rotation. Now, what you have to keep in mind is that x and y, or coordinates in local coordinate frame, do not change, right? They are the same because it's attached to rigid body. But coordinates in global coordinate frame change, right? Where the point is in global coordinate frame change after rotation. So what we want to do is that we want to write the new global coordinates, uppercase x2 and uppercase y2, based on local coordinates, right? x1 and y1, or x1 and x2 and y2, doesn't matter. x1, y1, x2, y2 in the coordinates in local coordinate frames are the same. So what we do is that we are writing, let me just put it here. So we want to find the new global coordinates, right, x2 and y2, uppercase, based on local coordinates. Right? Local coordinate, lowercase x and lowercase y. 1 or 2 doesn't matter because it's the same before and after rotation. So let's see, for x2, right, for x2, let's see what happens. X2 is lowercase x2 cosine alpha. I don't want to make it crowded here, but it's, see if I have right. Maybe I'll write it and then I'll erase it. So x2 is this part, lowercase x2 cosine alpha minus y2 minus this part. This part is right here. And this part is y2 sine alpha. Remember, if this is alpha, this is also alpha. Right? We have the rotation same. So x rotates alpha amount from where it was, and y also as a result rotates alpha amount. So this is x2 cosine alpha, and this is y2 sine alpha. So x2 uppercase x becomes, I'll go back to that, x2 cosine alpha minus y2 sine alpha. Again, we are writing new global coordinates based on local coordinates. So x2, the green, uppercase x2, is equal to x2 lowercase x2 cosine alpha minus lowercase y2 sine alpha. To find the difference, you will get where your x2 is. Same story for y2. So for y2, you will get y2 is equal to, let's see what we got there. For y2, lowercase x2 sine alpha, right, this is where y2 is. Right, this is what I'm trying to find. This value right here, y2. Remember, we are finding the new global coordinates based on our local coordinates. So y2 is equal to x2 sine alpha plus y2 cosine alpha. See if you see it. y2, global coordinate frame after rotation, y component of that, y2 is equal to x2 sine alpha plus, both of them are in positive sign, plus y2 cosine alpha. It's very crowded there, but I'm really trying to avoid adding more things there. I'll do it. Hopefully I remember to erase it. So if this becomes your x2 sine alpha, and for point 2 we have to go all the way right there. Oh, it's actually x, so I have to take it all the way to wherever x is. We are in that triangle, right? So here is the situation with x. This is x2 sine alpha, and this is y2 cosine alpha. So y2 is x2 sine alpha plus y2 cosine alpha. If you add them together, it gives you your new coordinate in y direction, in global coordinate frame. So it becomes x2 sine alpha plus y2 cosine alpha. Now for z2, well, z2 doesn't really change. So pretty much z2 is equal to z2, right? Because the rotation it's happening around z. You're still in the same plane. Doesn't matter what happened with x and y. I'm going to give you a few moments to look at this and see what happened there. Remember, the goal is to write the new global coordinates based on local coordinates. Now, local coordinates can be x1, y1, lowercase, or x2, y2, lowercase, because that doesn't change during the rotation. The point is attached to rigid body, and the frame is also attached to rigid body, so they rotate together. Right. So all I gotta do is to write this in a matrix form. So in the matrix form, we're going to end up having vector. I want to write this, right? New global coordinate frame, coordinate locations, or new global coordinates as local coordinates. Matrix there, and then this is x2, y2, z2. Remember, this could be or x1, y1, z1, because that doesn't change. So x to the first line of this matrix, x2, well, we said is x2 cosine alpha minus sine alpha and then 0. There is no z components. I'm writing x to the first line is basically the equation connecting x2 to global coordinate frame to x2 and y2 in local coordinate frames. y2, remember, first line multiplied by this vector gives you the first component. This is a 3 by 3 vector. A matrix is a 3 by 1 vector. This is also a 3 by 1 vector. y2 is sine alpha times x2 cosine alpha times y2 and nothing times z2. And we said z is the same, so 0, 0, 1. If you've seen rotation matrices before, this should be familiar. So this is the rotation matrix when we rotate alpha degrees or alpha amount around z-axis. We can write this in this way, in a shorter form. Right? This is R2 in global coordinate frame is R. We represent that as z and alpha, meaning the rotation matrix for rotation around z alpha amount multiplied by position vector in local coordinate frame. It can be 1 or 2. Again, I'll just use 2 as they're the same. So here is what you get for R. Let's define that. R z alpha, right? It is rotation matrix about rotation matrix for, let's put this for alpha degree, or I don't want to use degree, alpha amount, alpha rotation amount. I don't know, you get the point. Rotation amount about z-axis. So this is basically R z and alpha. Now, I don't do it, but similar procedure, you can find the rotation matrices for rotation. This should be up. For rotation about x and rotation about y. Similar procedure, just instead of x and y plane, look at x and z plane and look at y and z plane. You'll get the rotation matrices for those. So similarly, supposed to be similarly. Similarly, we can find r y, and let's call that rotation, that direction beta, refer to that, and r x gamma. Rotation around y, beta amount, rotation around x, gamma amount. So pretty much what I'm trying to give you at the end is this. R, z, and alpha is cosine alpha minus sine alpha 0, sine alpha, cosine alpha 0, and 0, 0, 1. Rotation about y-axis, beta amount, would give you cosine beta. If you do this process, you will get cosine beta 0. I think sine beta, I'm going to double check, sine beta, and then 0, 1, 0, and this becomes sine minus sine beta 0 cosine beta. Eventually, our x gamma gives you 1, 0, 0, 0, 0, cosine gamma minus sine gamma, sine gamma, cosine gamma. These are the equations you need to be. We're going to use them a lot. Right? That's why I spent some time deriving at least one of them. So, rotation about different axes. If you have rotation about x, remember we're talking about rotation kinematics, meaning the only type of motion that can happen is rotation. And pretty much you can represent any rotation using these three rotations. Whatever rotation you have in a different way, you just use the combination, this combination. One note that, again, I just give you without proving it, is that rotation matrix, these are matrices, depending on which axis you are having your rotation, about which axis you're having your rotation, are orthogonal. What does that mean? If you don't remember what orthogonal is, not a big deal. All you need to know is that because they're orthogonal, its transpose and its inverse, or their transpose and their inverse are equal. That helps a lot when we do reverse process and we want to go to local to global. So what I'm trying to say is that note, and it makes your life much easier. Imagine stuff every time you have to find the inverse of a 3x3 matrix, you can just find the transpose if you have a rotational matrix, and that it's much easier finding a transpose of a 3x3 matrix. Rotation matrix is orthogonal, which means its transpose and its inverse are the same. What I'm trying to say is that R, doesn't matter which axis, transpose is equal to R inverse. It's a very, very useful feature for rotation matrix. All right. So let's look at a couple of examples and see what do we mean, how do we use this. I think it's straightforward, but to make sure, I'm going to go over multiple examples. That's typically my approach in this course. I'll go over as many examples as I can and as possible to make sure that we just understand exactly what is going on in a class. Hopefully much less effort for you later in during the week if you want to study on your own. I typically, when I'm in a class, I say I want to make sure that you exactly know how to use or understand everything when you walk out of the class, but there is no walking out of the class. So Let's just start with something relatively straightforward. Example. We have a block, right? I'll bring the figure later. Let me write the problem statement. Find the position of the corner P with the coordinates of 5, 30, and 10 of the, oh, here is this, referring to that as a slab, of the slab after 30 degrees rotation about z-axis, followed by 30 degrees rotation about x-axis, and then 90 degrees, I can write it better now, 90 degrees rotation about y-axis. So here is the slab. I have to actually find it on my computer, but I did have the figure somewhere. Here you go. I have a better understanding of what's going on there. So here's the slab. What is this problem telling me? That I want you to rotate this 30 degrees about z-axis. This is global coordinate. Followed by 30 degrees rotation about x-axis, and then 90 degrees rotation about y-axis. Now, to get a better sense of what is going on there and what are we talking about, hopefully that doesn't make it more confusing, but more clear and less confusing. Here is what's happening. We have, first, we go from P1 to P2, 30 degrees around z-axis. And then wherever we are at that point, we follow that with a 30-degree rotation about x-axis. Right? We get to P3. That corner goes from P2 to P3. And then 90 degrees rotation about y-axis. So P3 gets to P4. If you have that 90 degrees around y-axis. All right, so we are following this point P, called P1 in this case. So remember, at the beginning, you have your coordinate frame x, z, x, y, z. Pretty much aligned with your global coordinate frame. Your body frame, your local coordinate frame is aligned with your global coordinate frame. It rotates, right? It's hard to show it on this one, but you can see the y-axis ends up being here. Z is still along this, and then you probably end up having your, I don't know why they use 2z there. This should be x. And your x ends up being probably somewhere, maybe to a better sense here. Right? This is from going from P1 to P2. Then again, your local coordinate frame moves from 2 to 3, P2 to, from position 2 to position 3, and then position 3 to position 4. Your global is still fixed, your local is attached to the body, so it moves with the body wherever it goes. That's the scenario that we're dealing with. So let's do it step by step. Step 1, we have the rotation about z-axis for 30 degrees. So let's be more organized. So P1, the position is 5, 30, and 10. Right? X is 5, Y is 30, Z is 10. The same in local and global at the beginning. So the rotation, first rotation, right? We have R rotation around Z for 30 degrees. So pretty much we plug in the values from what we had. Cosine alpha, basically right now alpha is 30 degrees, so cosine 30 minus sine 30 is 0, sine 30, cosine 30 is 0, and 0, 0, 1. Right? I'll just write it here. So cosine 30 degrees minus sine 30 degrees 0, sine 30 degrees, cosine 30 degrees 0, and then 0, 0, 1. So this means P2 is equal to, or let's write it the way we wrote before, or P2 in global coordinate frame is equal to, remember, this is just pretty much the relationship I put there. If you want to write it in a general form, R in global coordinate frame is R rotation matrix, whichever it is, multiplied by R in local coordinate frame. So this one is my R P1 in B, right? Because both coordinates are on top of each other at the beginning. So RP2 at G is RZ, well, not that Z, RZ 30 degrees times R P1B, right? Whatever the local coordinates were. You can just write it cosine 30 degrees minus sine 30 degrees 0. I'll just write everything down at the beginning so you know what's going on later on. We'll just use the notation 0, 0, 1 and multiply it by 5, 30, and 10. We do the multiplication, you'll get it's a 3 by 3 matrix times 3 by 1 vector. So we're going to end up having a 3 by 1 vector, which is the position of P in P at 2. So that'll give you if I got the numbers right, that should be minus 10.67, 28.48, and then 10 there. Right, so now it's the new position. Now in the new position, right, this RP2 in global coordinate frame is again the position in local coordinate frame. You have that. Let's put it this way. So you have the position there. This is your. Now again, I don't want to make it Y, Z, and let's say X. This is 30. This is very exaggerated 30s. Alpha amount, which is 30 degrees. Now in the new situation, again, you have the coordinate of P2, right? You know where it is, actually. Yeah. So you have, I think I made it crowded enough. So you have the coordinate of P2. Now what happens is that you want to rotate that another 30 degrees, about x-axis. What you care about is where it is. Let me just raise that. Now here's what you do. To make it easy, right, you stick with, you know where it is in global coordinate frame. So I will say, well, let's now in the new, forget about what happened in the first step. Now you have a block that is in P2. The coordinate is in P2. right? You can stick the basically with your old local coordinate frame, but to make it easier and even possible, we have to say, you look at it as a fresh problem. Now you have a block that you know its coordinates in the coordinate of one corner, and you still bring back your local coordinate frame where it was, y, z. Technically, your local coordinate frame moved with your body, right? But that was for previous motion. Now, fresh, we have a block that is coordinated, forget about P1, P3, and P4. Its corner is on P2. So we have a local coordinate frame aligned with global coordinate frame. Again, in this local coordinate frame, you know where the position of P2 is. P2. Right? This is the position of P2. Because your new global local coordinate frame is aligned with your global coordinate frame again. Right? In phase 2, this is step 2. In a step 2, now you just stick the new local coordinate frame aligned with global coordinate frame. Why do we do that? Because we already know what the position of P2 is in global coordinate frame, and we know the rotation is happening around z-axis for local global coordinate frame, or in this case x-axis, part 2. So here's part 2. This is the rotation I'm doing right now about x-axis. So in this step, so step 1, step 2. Now what do I have? I have slab. I know where its corner is. I know exact location that I found from previous step. I want to rotate this slab 30 degrees about x-axis. So here is R. I have to find Rx 30 degrees. Going back, what was Rx 30 degrees? Now you can think about the 30s as beta, so as gamma. Right? So 1, 0, 0, 0, 0, then gamma is 30 degrees. So we have 1, 0, 0, 0, 0. This becomes cosine 30 degrees minus sine 30 degrees, sine 30 degrees, cosine 30 degrees. This is the rotation matrix. So in this form, again, you get R P3. Remember, we're going from P2 to P3. In global coordinate frame is R P rotation matrix, which is R X 30 degrees times position of point 2 in local coordinate frame for step 2. Right? You do this multiplication, you'll get the number. So remember, this is your RP2 now. This is your RP2, and this is your matrix. If you do that multiplication, you will get minus 10 point, well, the first one doesn't change, 6, 7. You're rotating around x-axis, so x doesn't change. 19.66 and 22.9. This becomes the position. This is step 2. Now step 3. All right? What do we do with step 3? Step 3, let me bring that figure here again. For this step, the same story. Right? Now, you bring back your local coordinate frame aligned with global coordinate frame. This is your B. and this is where you are, and you know exactly the coordinate for P3. The coordinate for P3 is what you got from step 2. Right? This is R P3, and this is R P2. So now you have a slab, and this is your slab right now. This is your slab. You know where it is in local coordinate frame and global coordinate frame, because you aligned your new local coordinate frame with your global coordinate frame. And what happens is that you have a rotation of 90 degrees about y-axis, global y. Right? So wherever you are at the moment, you have to rotate that for y, 90 degrees. This direction, 90 degrees. So this is the situation. You have R. So what you need is a rotation around y for 90 degrees, that matrix. Going back, this matrix was, right now beta is 90 degrees if you think about rotation about y. Cosine 90, 0, sine 90, minus sine 90, cosine 90. So I'll do that here. So there'll be cosine 90 degrees, 0, sine 90 degrees, 0, 1, 0, minus sine 90 degrees, 0, cosine 90 degrees. This is your rotation matrix. So R at point 4 in global coordinate frame is rotation matrix for 90 degrees times R at point 3 local coordinate frame. Local coordinate frame for this step, right? What you got from before. So this is, I can plug in at least that one, 90 multiplied by the value you got from before. So you got, what do we get? We get 1067, 1966, 22.9. So 1067, 1966, and 22.9. This is 19. All right. So this will give you 22.9, 19.66, 10.67. That is where your corner is, or P4. Obviously in global coordinate. So this example included 3 steps, right? What we learned was just for 1 step. Keep in mind, for 1 step, we know if we know local and local and global coordinate frames are aligned at the beginning of the motion, and then we can have a rotation around any of those axes in global coordinate frame and find out where we are in global coordinate frame at the end of the rotation. This is what we learned. Now, this example is for practice, to do it 3 times. Step 1, slab is just on laying down there. You have your local coordinate frame B right there, right? And your global coordinate frame. Right? They're aligned, as we said at the beginning. You have to rotate the slab 30 degrees about z-axis. So you rotate that, and we found the relationship. We found figure out how can we find the coordinate of a point in global coordinate frame, like as long as it rotates around any of those global axes. In this case, 30 degree rotation. You find where this slab is at the end. So your slab is going to be somewhere like this, in this position, right, after rotation. And obviously your local coordinate frame is rotated, right? It's y, z, x. Now you're done. This is, you use what we learned. Now go to step 2. Now you have a slab that is sitting in that position, global coordinate frame, and you want to find out if you rotate that about z-axis global coordinate frame, where does it go? Well, I'll bring back the local coordinate frame aligned with global coordinate frame, and I know where the position of that corner point at the corner is in global and local, because now local is aligned with global, and rotate that for 30 degrees around x-axis, and I find that one. So in this case, your final local coordinate frame becomes, if you think about rotation around x, it becomes somewhere, this x is still here, but the coordinate shouldn't change, so maybe I should make it clear so it's not confusing. This goes all the way to here. This is z, and this is x. Yeah, it definitely made it more confusing there, but I hope you follow that is what I said. My writing is not as let me erase that. It's not as clear as I want it to be. In this case, let's follow in this case. In this case, x is still there. We have rotation around x. So what happens is that you get to have y there and z there. Right? Y there and z there. So what happens after rotation? 30 degrees around x-axis. Again, done. You use what you learned to find where the point is after the second rotation. Step 3. Now you're going to have a slab. The corner is point P3. You have x, y, z coordinate global coordinate frames and x, y, z local coordinate frame. You put the new local coordinate frame, or for this step, again, erase what happened. Now you have a slab like this. You start with local coordinate frame aligned with global coordinate frame. And now you know you have a rotation around y-axis, y global coordinate frame, y 90 degrees. You make that rotation and you find out where the point P3 is, which becomes P4 at the end of that rotation. So if you do that rotation, in this case, this becomes rotation around y. Your y stays the same. You get x and z. This is going to be your new after rotation local coordinate frame, because your local coordinate frame is attached to your slab. All right, I'll go over a couple more examples. Just a first one. I'll go over to three more examples in next class about rotation kinematics to get a sense of what happens there when we use rotation kinematics. One thing, the reason we went over this step by step, I'll mention this, I'll go over this example, I'll mention that next class, that you will see when you have a series of rotations, you don't have to do it step by step. You can just multiply rotation matrices and find what happens going from first step to last step. As a matter of fact, this, if you do the multiplication, you will see that P4 is equal to R, the last rotation, which is 90 degrees, times the second to last, which is 30 degrees, times R Z 30 degrees, multiplied by P1. So this is a relationship you'll see. We'll talk about that. But for a series of rotations, you don't have to do it step by step. You can just do it by multiplying rotation matrices and then find the final position of the point. I'll go over this again next.